completely different from my previous talk in the thing, because I'm not trying to be very precise with symbolic methods and so on.
I know Joseph likes to keep the door open because there's air, but sometimes the noise.
You should really open the door and because we also have people.
Just that people are talking. There are people talking too much over there.
Oh, all right.
So sorry.
Okay, so the background to this whole thing is that natural language processing over the last decades had a lot of impressive advantages even before large language models came around. And we claim that a large part of that, why that happened, is because they had lots of data sets, benchmarks, tasks, competitions, all these kinds of things. And they really benefited from that. We want to do the same thing for mathematical language, and that comes with some unique challenges. That means we can't just literally copy what they did. We have formulas, we have tables, so we don't just have Unicode strings, we have something more rich, and that means we can't, we have some extra challenges. Before I talk about my thoughts of addressing that, why do I care about these things, why do I want that? My answer is semantic services. With that I mean, I'll show you a few examples, just ideas, what would be nice to have. One example would be formula search. Maybe I search for an energy of 1.5 electron volts in a particular type of paper to see if other people found the same phenomenon or something. And then I want to find maybe something like this, 1.43 plus minus some electron volts, which is a very different string. So, or we find something in joules, which looks again completely different, but they're of course conceptually matching. So we need some understanding that this is joules and how we can convert it and these kinds of things. Or if we search for a formula, we might want to know that the k here can be alpha renamed. exp is the exponential function, which is the same as e to the power of, if this is Euler's number. So we need some information.
It comes back, yeah.
Yeah, good. A bit confusing. Another example is, here's an excerpt from a paper about solar panels and their efficiency. And there's a formula you might be interested in, and there's the x with a funny symbol, and you don't know what that is. If you pay close attention, the page earlier it was mentioned somewhere in the paragraph, but when I read it, I missed that bit. So it would be nice to just hover over it and say, wait, where was this mentioned before? What is it? And then you find out it's the sun's air mass. But then we need to link these things. Ideally, we can also link it to an explanation of what that is, because it's not a very intuitive word. It's the amount of air that the light travels through until it hits the solar panel. Or there's also a relative variant of that. Anyway, so that would help us with reading a paper. We might want to just compute things that would be even more ambitious, just plug in some values, maybe make a plot for our setting or something like that. All these things have in common that we need to have some level of understanding, some semantic annotations. This x here is the same as that x there, and so on. But we don't need a full formalization. We don't need to have the paper in lean. Some semantic annotations already help us a lot. Okay, good. So we have, the other problem is, of course, we don't have this information. Authors don't provide it usually. STEC is an approach to change that. But we have millions of papers that did not use STEC. And we also don't want to do it manually, add this information. That's just too much work. So we would like to automatically infer them. One way we like to think about it is we like to think of the spotters that find specific semantic phenomena. You might have a paragraph classification spotter that says, this is a definition, this is a theorem, that's a proof. Might have a declaration spotter that says here the x was declared as the sun's air mass or something like that. Maybe something for units, so that we can do the conversions. And these spotters can actually support each other. For example, if we know that here an m is introduced as a natural number or something, then the km here can't be kilometers. So actually we can use results and then maybe get better results if we use the results from other spotters. And accumulate more and more understanding of what's in these documents over time. That fit? Okay, so what's the problem? Why has this not really materialized? We've tried a few times, but it didn't get very far. One challenge is actually getting a corpus. There are some good options by now. So I used usually what's created by Dan Ginnef, the archive.ml or now R5 corpus. It's really good. It has most of the archive documents in HTML, which makes it relatively easy to process. And so we asked students sometimes to write a spotter, look for units, for example, and they never got very far. And one problem is that they sort of had to reinvent the wheel very often. They might need a plain text representation to use normal natural language processing tools. They need to store the annotations somehow. They need to create a manual annotation data set for evaluation, testing. And doing that on these documents usually means you want to do it in the browser, you need to do some JavaScript coding to mark things. That's a lot of work. And then there's little time left to do the interesting work of actually implementing something that finds these things. And the other challenge is that we often cannot reuse the work from other people because there's no standard way of doing these things. So they might modify the documents to store the annotations, they invent their own format, and it's all getting really incompatible. So just as an example, here's a definition. A multiset over a set X is a function m from x to n. If we have it in HTML, it's a bit simplified here, but we would have some sort of HTML code with mathml maybe for the formula. And then a person says, okay, I'm going to annotate things and I'm just going to write it into the document. I'm going to put a span around the word that's being defined here, and then we know what's defined. We can highlight it in the browser maybe, something like that. Another person maybe has the same idea, wants to also find what gets defined, and says, I'm going to use machine learning. I'm going to make a machine learning data set. I'm going to create strings. I'm going to remove all the text, replace formulas with tokens maybe, and make a data set like this. Maybe a third person says, I'm going to store it externally. I'm going to use an XPath to point to the thing that's being defined. And now the problem is all of this is incompatible. So, for example, this XPath does not work for the first document anymore because we changed the document. This one here is not even XML-based anymore, so it's all incompatible and we can't compare things. We can't reuse test data sets, training data sets, or just use it to build on top of it easily. So, we tried to figure out how to fix that. So we sort of, that's from I mentioned that in a previous Kickham talk. So we want to develop some sort of standard to have all these things reusable. And we started proposing something, experimenting with that. And so it's a good time to hear from people what they think about it. This whole thing is based on the research description framework. So it's great that Stefania talked already about all these knowledge graphs. We want to use that. It means we have databases, query languages, serialization formats, all of this is already readily available. And in particular, there's a W3C web annotation recommendation, so we can basically use that, adapt it a bit to make it work for these things. So I want to briefly show you the rough idea of it. According to this recommendation, we make a node for each annotation, and then we can attach information to it. Who created it? When, if we want to have these kinds of meta information. And then there's a target and a body that carry the main information. The target says, this bit of the paper I want to annotate. And the body says, I want to attach this kind of information to it. So for example, you could say here, the bipartite graph that's occurring here in the document, I want to annotate it with a Wikidata tag for it. Something like that. It's not completely straightforward how to do this target, but there are some recommendations. It's a bit complex, so you get a somewhat largish graph where you reference the document and have some selectors, but I don't want to go into too much detail because I don't have that much time. So we've tried this out, experimented a bit with it, and so the first thing was to just import existing data sets. So there was a quantity expression data set, there was a formula grounding data set, and a paragraph classification data set, which we actually had to recreate. But the thing is, all of them are incompatible already, so they are not linked because they are based on different variants of the documents, but you can import them and you can represent them using this. And then to further test it, we just created some prototype spotters. Part of speech tagger is more for load testing maybe. I think that's not the most interesting thing. References to math concepts, variable declarations. By now we have a few more already. And try to do scalability testing. So we ran 2 spotters over 100,000 documents. That resulted in 50 million annotations, 800 million triples, And you can load it into Triple Store, but it takes a while, at least when I did it. And if we have all this data in one place, then we can do querying. So for example, we can say, give me all the papers about group theory that have theorems that mention rational numbers. The query is quite long, you probably usually wouldn't want to write it by hand, but this kind of thing is possible already, and you could just make a nicer interface for this. You don't have to write Sparkle. Okay. And then you can start developing tools that are based on this idea, so that you don't have to do your own annotation tool. So what one of our master students did is he developed something we call Annotize, which is just a browser thing where you can load some JavaScript and then you can annotate the documents. So you can highlight something and say, I'm going to make an annotation, and it visualizes them. You can configure it a bit. So here we see we have paragraphs highlighted, the theorems in this case, concepts that are linked, and so on. So you can make a test data set, for example, or look at the outputs of your spotter. Okay, I'm way too fast. So we also have some Python code for just working with these annotations for the spotter base. It does things like normalizing annotations. It can generate different plaintext representations in a way that they're linked to the original document. That's always the challenge. So we want to be able to create some plaintext and remember for each letter where does it come from. And then you can work on the plaintext. I don't know, do a dependency parse, find interesting things, and then go back and annotate the original document. And we have some ways of working with JSON instead. If you don't know about RDF, don't like it, don't want to get into it, you can also just use JSON for import and export, and it will be converted. Okay. So the whole talk was because it was suggested that I should have a work group about this on Friday, the second work group, I think. And there are different ideas, depending on what people are interested in. So one thing would be we could together implement a very simple spotter for declarations, saying the K here is declared, the WK here we would have to go a bit into formulas. That would be just to see a little bit how these things could go, and to see the different tools, how to visualize it, either together or just me showing it, depending on what's interesting. We could try to then develop a more interesting spotter, something that actually does interesting work, or we could just discuss what kinds of annotations are actually useful or what might be difficulties with this format. Yes, so that would be my proposal for that. And so to conclude, I talked about this annotation standard for STEM documents based on semantic web technologies. It's intended to be compatible with a wide range of annotation tasks. Because we have this knowledge graphs, it means we can, if we have the annotation board, we can put any graph in there. It doesn't just have to be a tag, it could be more complex information. We want to use it for creating data sets, benchmarks, and so on that are reusable for different people, doing completely different things, and then have an ecosystem of tools that support this. And ultimately, the long-term goal is that we want to have semantic services that then use this data in whatever ways. Yeah.
Great, thank you.